Do you hear that? Let's try that again. What just happened? Well, sound. Beats. Beats is what just happened. If you want, you can actually go back and count how often you heard the sound pulse get loud and quiet, loud and quiet. And what you're hearing is constructive and destructive interference. It gets loud with constructive interference and quiet with destructive. When the frequencies are only off by 1 hertz, 1 wave per second, you hear woo, 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 woo. You hear 1 pulse every second. When they're off by 2, woo, 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 you hear 2 per second. 3, it's faster, and so on. After about 10, you can't really count anymore. Counting tenths of a second is pretty tough. Okay, well, so let's take a look at today. We're going to explore sound. I've got 3 goals. We got a Zoom meeting today at 11. I'll put some details up later in the morning. And if you miss it, we're going to be talking about this. So goals: identify properties of sound waves from musical instruments using principles of wave interactions. That's fancy lingo for we're going to look at constructive and destructive interference as it relates to musical instruments. We're going to define beats as they relate to interference. So that's what I was just talking about. And we're going to look at a spectrograph to determine if a sound is composed of one frequency, like, say, a stringed instrument, or a combination of frequencies, like maybe a tuba or some other kind of horn. So you've got to warm up here, and you've got 3 images, and you're supposed to draw all 3. And then for each one, you're supposed to think about how the red and the blue lines would interfere with each other. Would it be constructive or destructive, given what you see from this resultant here, the green line? So if you haven't done that yet, go ahead and do it now. Pause, unpause, and come on back. So this first one here, the 2 lines are almost in the exact same place, which means they're going to build up each other. And we talked about 5 plus 5 being 10. And so that's what we see here, right? Each of these goes to this line. We could call this line 5. If we have 5 and then another 5, that's going to be 10. Same thing here. Even though it's upside down, it's the same idea. These are 2 troughs. And so -5 plus -5, what's that? -10. Here, we've got something different. We've got +5 here, -5 there. And so add those together and you get a big goose egg, 0. Okay, so that's it with that. Questions? Remind app. And here we go. So let's see if this works. Okay, so there's the warm-up that we just did. You should write down some notes about wave interactions for today in your notebook. So let's move me. So we've talked about interference a lot. And so this is when we got the definition right here. I'll let you read it on your own. But the idea here is that sometimes these waves are going to line up to give you constructive interference, that's CI, and sometimes they're going to line up to give you destructive interference. There's a lot of waves here with both these, and it's kind of hard to tell where they line up. But if you were to take a piece of paper and stick it on your phone or something like this, and stick it on your phone or on your laptop or whatever it is that you have. If you line it up vertically, okay, like this on this image, all right, so I'll show you with my cursor. If you line this up, you can see, like for this one, the peak here, if you go straight down, lines up with another peak perfectly. The other ones don't. Sometimes a peak like here lines up really well with a trough, and so you get destructive interference. So we've got all these periods. So like this, each of these would be a beat. Right? We don't know how much time goes by here, but each of these would be a beat. So this would be loud, quiet, loud, quiet, loud. That's what we're showing here. So this is interference. Okay. So we're talking about that. I gotta make myself small. Okay. So here we can see some nodes and antinodes. And if this is confusing to you, go back and watch the Flippin' Physics video. I forgot to link it, but I'll put it right down here. We watched it earlier last week, and it talks about nodes and antinodes. And this is areas of compression and rarefaction. This is sound waves. Where they're compressed, it's dark. Where they're rare, it's light. And when those dark areas overlap, you get areas of increased compression. So think about what you would hear. Right? What would you hear if there was a destructive interference going on? You'd hear nothing. It'd be quiet. So how does this, what's the real world applications of that? Well, noise canceling headphones is one. Concert halls to reduce interference that that destroys the sound. You want to boost the sound. And you can actually make this happen in your house. So I've got this diagram here. And what we usually do in class is we take my stereo, right? Remember the stereo that was under my desk? So we take that stereo and I just move the speakers about 6 feet apart. And I turn on that same sound generator that I had at the beginning of class, which actually I have a link to right here. Okay. And so what I have everybody do is stand up, go to the back of the room, and just spread out. And very slowly, so we pick a tone that you can hear, say 400 hertz. Turn up the volume. And very slowly walk around the room. And if the speakers are spaced far enough apart, what you get is this. You get these waves that are coming out. That's what the sound is. It's waves. And so every sound is going to have high and low spots as that wave moves through space. And so here's an example of a high spot. And then this light line is an example of a low spot. And there's going to be these points in the room where a high spot in the wave from this right speaker and a high spot from this left speaker where they interact, like right there. And here's another one here, another one there. Right? There's a bunch of them. And you're also going to have spots where highs and lows interact, like here and here. So if you walk very slowly around the room, you'll notice these spots. I'm going to try and do this with my kids tomorrow and post a follow-up video, see if they can handle it at 3 and 5 years old. But you'll notice it, and you'll feel it. You'll feel the pressure in your ears. It's really kind of phenomenal. And what you're hearing is areas of compression, right, that's the dark line, and areas of rarefaction, that's the light line. And when they are opposite each other, but in the same space, they kill each other. They cancel out. Destructive interference. So you can hear it. It's noise canceling. Right? That's how noise canceling headphones work. So really cool stuff. You should try it out. When you hear music, it's a mix of frequencies. So you're hearing constructive interference. Right? You're hearing beats. And those combinations of frequencies. Say you play the trombone, it's not just one sound that comes out of there, it's multiple sounds, and they combine to get you beats. And those beats aren't always like do, 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 or boom, 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 boom. Usually they're a lot faster than that, but it's this combination of all these frequencies that gets you this really rich sound. And so what we see here with these two frequencies, just for example, 9 hertz and 11 hertz, every once in a while, they're going to line up, all right, twice a second, because they're off by 2 waves per second. So 2 times per second, they're going to line up, either with 2 troughs like here, or with 2 peaks like here. All right, so this happens twice every second. All right, we're starting at 0. It happens once, and then twice, and then repeats. So if you want to figure out the number of beats per second, you would just subtract the 2 frequencies, right? 11 minus 9, what's that? 2. Woo, 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 woo. And again, musical instruments take advantage of frequencies that are much larger than this. Usually, you don't really hear that woo, 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 remember, because you can't count the number of beats above about 10 per second. Usually what you're hearing is in the multiple hundreds of beats per second. And that makes this really full, rich sound, which we'll hear at the end. Okay. So what are beats? Lots of things to read about here. Again, just to be clear, beats are not the of a drum. That's different. So you can play around with the sound generator. And again, if you have access to 2 devices, you can open the sound generator in both and you can make beats. This guy right here, the one that I used earlier, works great on your computer device. I downloaded this thing called Sonic on my phone. I don't recall if this works on phones or not, but the way it works is you click play. You've got a volume here. You can stop whenever you want. There are tones that you can pull up here. You can choose whatever you want if you're into music. And you can increase this by 1. You can tap, and you can choose whatever you want. Just keep in mind that if you're on a computer, this won't work very well. It's playing right now, but the speakers don't do bass very well. Your headphones, though, probably will. Another thing to watch out for is if you... That's loud. It's interesting. We perceive higher frequencies as being louder even when they're actually at the same amplitude, the same volume level. It's probably kind of annoying. Watch out as you get into the really high frequencies. It's probably hard to hear that. But if you turn this up really loud to hear it better, it can actually damage your hearing. So make sure you keep the volume low. Depending on how you listen to music and your biology, you may top out somewhere around 14 or 15,000. Some of you can hear a little bit higher. Some of you think you're hearing stuff, but you're just imagining it. It really depends. Anyway, this simulator is really cool. And stop. Okay, if you want to use this one, it's called Sonic, and it's a free download. And you can swipe up and down. It's really kind of challenging to get it to the right spot. So usually I just get this one to something or close to 400, and then I move this one around. This is the one that I adjust, because this thing is challenging to do. See, it's fussy. Okay, back to here. So, moving along. There we go. Some things have natural frequencies. Stringed instruments, some things tend to vibrate at single frequency. A flute is another example. Other things have sets of frequencies. And so these depend on the medium that we're in and the wavelength of those. So here's an example of something that's at a set frequency, and things that have a combination. And so I wanted you to think about how a spectrogram gives you a visual, right? Remember gram, like Instagram? Gram means record. Right? So a record could be notes. It could be a picture. In this case, it's a picture. A spectro record. Right? It's a visual spectrum record. And so that's what spectrogram means. And we're going to look at how these different things vibrate as a set of frequencies. So you can see this. And if you click on the link, this is a really cool thing. You can listen to all these different sounds. Let's move me out of the way. So you can turn on your microphone. Hello? Hello? That didn't work. So pretty much one frequency here. And it changes depending on your fingering, right? But for each little fingering hole, there's one frequency. What about here? Single or multiple? And I'm talking about for each pluck of a string. Does each pluck make a single sound or multiple sounds? That's different. Is that a single frequency or multiple? It's multiple. This is why beats are sometimes really highly protected. A isn't just a single frequency. It's not just a single sound. It's a combination of lots of different tones that takes a lot of work to get. Some of these things are highly guarded. It's a cool sound. Been hearing lots of this lately. Wow. This is somebody rubbing their finger on the rim of a glass, and then another glass, and then another one, all with different amounts of water in them. If your speaker is enabled, you can use this, and I thought you could, there we go. Single. Single. Crazy. Hello? Ah, there it is. There's my voice. Look at that combination of sounds. Hello. 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 See? Look at all the fun you can have with this. We should have just done the whole thing like this. Okay, so there's some follow-up questions that go along with this. Goodbye, spectrogram. Enjoy. Hope you have fun with that. So, think about which ones are most like the flute, most like the trombone, most different from either. Try to classify them as single frequency or combination of frequencies. And normally we'd share out, but thanks to COVID-19, you get to share with yourself. Sit in front of a mirror. Okay, last thing. Try and make something that has 2 beats, 4 beats, 5 beats, 9, 10, 12, 15. So there's a little Beats Interactive you can use, or you can do what I showed you, earlier. And that would be, right, using 2 things with sound generators to make those beats. So that's it. We're going to stop right there. Tomorrow we'll continue on with harmonics and fundamental frequencies. And if you have no idea what these are, go back to last week and watch the Flippin' Physics video on harmonics. It was his video on how music shows up in sound. Okay, that's it. Have a great day. See you later. Still here? Okay, goodbye for real.